All right, next some terminology stuff. When we're talking about sets, we want to talk about equality of sets. And it means exactly what you would think it would mean. Two sets are considered to be equal if and only if they have exactly the same elements. Therefore, if A and B are sets, then A and B are equal. So A and B are going to be equal if and only if for every x, x is in A, if and only if x is in B. Okay, so we're using that universal quantifier and logical connector notation that we talked about from chapter 1. So A and B are equal if and only if for every x, x is in A, if and only if x is in B. And then we write with an equal sign if they are. So A is equal to B if A and B are equal sets. Now, Venn diagrams. I'm sure you're familiar with Venn diagrams from other classes, but if not, here's a quick explanation and a refresher if you are. One thing that I'm going to insist on is I want you to always draw your universal set, because sets don't live in a vacuum. We usually want to consider sets as being part of a universal set, which is the universe of everything under consideration. And when it comes to Venn diagrams, that's what this rectangle is on the outside. So always draw your rectangle to indicate your universal set. This will become important in just a few minutes when we talk about complements. So I have a universal set U, which is all the letters of the alphabet. So I draw a box to indicate my universe and label it with a U. And then I could consider a smaller set that's inside of my universe. I'll call that set V. And this is just all the letters that are vowels, A, E, I, O, and U. So I have a circle, and then I have a dot for all of my vowels, A, E, I, O, and U. So this is a Venn diagram. You have a box for a universal set, and you have circles indicating smaller sets inside your universal set. Now, if you have two sets, you can define something called subsets if a certain condition is met. Now, here is the notation we use. This A with this hook with a line under it, B, that means A is a subset of B. So when you see that notation, A is a subset of B. That's what that notation right there means. And what it means mathematically or logically is that for everything inside, for every x, if x is inside of A, x is also inside of B. But that means if you want to show A is not a subset of B, you have to find one thing inside of A that is not inside of B. So let me draw some Venn diagrams to kind of illustrate these two ideas. So first I draw, whoops, don't want to do that. First I draw my universe. This is my universal set U. And I have my bigger set B and my smaller set A. So when this happens, let's draw A right here. When this is a situation, A is indeed a subset of B because A is totally contained in A. Excuse me, A is totally contained in B. Now I want to show you two examples of where A is not a subset of B. Here's the first one. So here's my big set B, and here's my set A. So obviously A is not inside of B. So A isn't a subset of B. But here's something else that can happen when A would not be a subset of B. Here's my set B, and here's my set A. Okay. Now, some elements of A are inside of B. I have this right here. These things are what are common to both A and B. So some of the elements of A are inside of B, but not all of them. And since not all of them are, that means that in both of these cases, A is not a subset of B. Now this simple-looking theorem actually turns out to be pretty important in a lot of different ways that we'll get into. and a lot of different ways that we won't get into. Actually, I was teaching a class for math majors called topology, and this idea came up for one of our really, really important ideas. So this isn't something that's just, it's just kind of a throwaway thing. It is important, it does show up a lot. But let's look at it. I have a theorem that says two different things. Theorem says, for every set S, number one, the empty set, that is actually a typo that I just noticed. What that should actually say, let me black this out. What that should say is, for every set S, the empty set is a subset of S, not an element. I apologize for that. I just now noticed that. So that's also wrong on the notes. So I'll have to make that correction to the D2L notes. At any rate, for every set S, the empty set is a subset of S, and S is a subset of itself. Well, let's check the definition and see if that's true. So recall the definition. A is a subset of B if for every X in A, we have that X is also in B. So what would that say for the first part of that theorem? What would that say when we're considering the empty set? Well, the empty set would be a subset of a set S if for any element inside the empty set, then that element is going to be inside of S. Okay, but you're thinking, Dr. Roberts, that doesn't make any sense because the empty set is the empty set. It doesn't contain any members. It doesn't contain anything at all. So, and I say you're right, but here's what you need to keep in mind. This is an implication. This is an if-then statement. So that means the first part of this statement is false. Okay? So I'm saying false implies either true or false, depending on whether or not X is actually an element of S. Remember what we did with truth tables. For an implication, the only time an implication is false is when we have true implies a false. So here I have false implies either true if X is an S, or false implies a false if X is not an S. But it doesn't matter. It doesn't matter which one of those actually is the case, because this whole implication is going to be true because I'm starting with a false statement. That means that for every X in the empty set, if X is in the empty set, then X is an S. That is a true implication statement. That is a true conditional. That means since this is a true conditional, that means yes, it is the case that the empty set is a subset of S because this is a true statement. It's weird, right? Now the second part of the theorem, don't want to use that color. The second part of the theorem is easy because it just says that X is a subset of itself. Well, if I have an element inside of S, then yep, it's certainly true that X is an element of S. Let me go ahead and fix that. X is an element of S. So yeah, we do get that S is a subset of itself, because anytime I take something in S, that something is an S, so S is a subset of itself. Not as weird as saying the empty set is a subset of S, but nevertheless, that's still the case.